All right, lecture 18A today. We'll do more external direct product, isomorphism facts, and computations as well. Remind you what a normal subgroup is. Probably most of lecture 18B will be something related to normal subgroups, factor groups, often called quotient groups. In fact, I learned them as quotient groups, so I have to work hard at saying factor group instead of quotient group. But our text uses the terminology factor group. So again, we have this criterion for when the external direct product of two cyclic groups is also cyclic. And that is when the orders of each of the things in the factor, these are finite cyclic groups, when those orders are relatively prime. Okay, so take another example here. The external direct product of Z4 with Z9. 4 and 9 are relatively prime. This is going to be isomorphic to Z36. Maybe to help believe that, let's go ahead and make a table of the possible orders. So elements in Z4's the external direct product with Z9 are going to be ordered pairs. A comma B, where A is in Z4 and B is in Z9. So we can make a table of the possibilities of the orders for A, the orders for B, their least common multiples. And then based on that, and also thinking about the Euler phi function, we can also count the number of elements of each of the possible orders. Of course, you always have the identity. There's only one possible identity. In this case, both A and B are going to be 0 with the identity. A could have order 2 or 4, so I could do this kind of thing. The least common multiple of 2 and 1 is 2. The least common multiple of 4 and 1 is 4. How many elements of order 2 and how many elements of order 4? There's only one element of order 2 in Z4, right? Think carefully here. This is representing an element of order 2. For A in Z4, 2 is the only element of order 2. There's only one element of order 1 in Z9, that's 0. Altogether you have 1 times 1, one element of order 2 coming from this combination. 2 elements of order 4 coming from this combination because there's 2 elements of order 4 in Z4. 1 and 3, the generators of Z4. Only one possibility for B, so you have 2 times 1 or 2 possibilities there. The order of B could be 3 or 9. That's the other possibilities. Least common multiple of 1 and 3 is 3, of 2 and 3 is 6, of 4 and 3 is going to be 12. Least common multiple of 1 and 9 is 9, 2 and 9 would be 18, and 4 and 9 would be 36. Order 36 there. This is going to be cyclic. Let's go ahead and do that one first. 2 elements of order 4. How many elements of order 9 would be in Z9? 6. Yeah. Generators of Z9 are going to be 1, 2, 4, 5, 7, and 8. These are the generators of Z9. There's 6 of them. Euler phi of 9 is 6. So altogether you have 2 times 6 or 12 elements of order 36 in this. And that feels wrong. Is that correct or wrong? For some reason that feels wrong. Let me think here. No, I guess that's right. That seem right? Okay. Let's double check it with the other ones. Let's go up this way. One element of order 2 in Z4. Again, 6 elements of order 9. This gives 6 possibilities here. Here and here we got 1 times 6 as well. There's 2 elements of order 3 in Z9. Euler phi of 3 is 2. They would be what? 3 and 6. the elements in the Z9 that have order 3. 2 of them there, 1, 1, and 2 here. We get 1 times 2, 1 times 2, and 2 times 2. Might be better to organize these tables by the orders, and I think I will do that with the next example. How many elements of order 2? There's just one of them. How many elements of order 3? There are 2 of them. I guess we aren't getting repeats here. Sometimes you get repeats. Altogether, these should add up to 36, the number of elements, and we do have generators. We've got 12 generators, so it is a cyclic group. 1, 2, 4, 6, 8, 18, with the 4 and 6, 24, 36. The total is 36 here. As it should be, this has got 36 elements. What's an example of a generator? Anything where A has order 4 and B has order 9. So for example, 1, 1 is a generator. 3, 1. 3, 5 is another example of a generator. Where the A has order 4 and the B has order 9. Okay? Shouldn't be surprising by this theorem, 4 and 9 are relatively prime. This result can be extended to the external direct product of a finite number of finite cyclic groups, not just 2. We can do this extension to 3. So, for example, we have the external direct product of, say, those 3 groups. 2, 3, and 25 are all relatively prime. So this is going to be cyclic. It's going to be isomorphic to Z sub the product of these numbers. 2 times 3 is 6 times 25 is going to be 150. That's a cyclic group of order 150. But this is an if and only if. Anytime the groups have, in the external direct product, have orders that are not relatively prime, like 4 and 6, this is not going to be cyclic. You could say, you could break up the Z6 into a Z2 external direct product with Z3. You could say it's isomorphic to this, if you wanted to. But it's probably best to have the external direct product in with the fewest number of factors anyway. But it's not cyclic. There's going to be no element of order 24. There's no way to get a least common multiple of the orders of the elements to equal 24. Think about the orders of the elements in this one being 1, 2, and 4, and this one being 1, 2, 3, and 6. Yeah, there's no way to get a least common multiple equal to 24. Let's do one more example where we make a big table to try to figure out the number of elements of the various orders. And I think with an example like this, it's going to be best to order these things by the least common multiple possibilities. So in other words, I'm going to think about all possible combinations of A and B that give me least common multiples here of orders 1 first, then 2, then 4, then 8. Again, quickly we can write down the identity. What ways can we get a least common multiple of 2? Those 3 ways. And in each case, the number of elements is 1. So altogether, we're going to have 3 elements of order 2. How about the elements of order 4? We can get the elements of order 4 in those ways. In each case, the least common multiple is 4. But the number of elements in each category is not necessarily the same. Be careful. With 4 and 1, we get 2 times 1. But with 4 and 4, we get 2 times 2. Add those up, 2, 4, 8, 10, 12. Altogether we have 12 elements of order what? 4, yeah. Looking at the least common multiple. And finally, you're not going to have any elements higher than order 8 here. The elements of order 8 are going to come from combinations like these. You see that down there?
Yep.
Okay. Least common multiple in each case is 8. These are going to be the categories that give you elements of order 8. Four times 1 is 4. 4 times 1 is 4. Careful. 4 times 2 is 8. 4 times 4. Right? There's 4 elements of order 8 in Z8 in both spots there. So you're going to get 16 elements from that one. Then 8, then 4, then 4. Add those together. 4, 8, 16, 32, 40, 48 elements of order 8. Do these all add up to 64? 48 plus 12 is 60, 63, 64. We've accounted for all 64 elements. As you know from chapter 8, there are facts about isomorphism classes for the group of units modulo n. There's this important fact, that once again, if S and T here now are relatively prime, then U of S times T is isomorphic to the external direct product of US and UT. Symbolically, you can write that. And this can be extended to U of a number that is a product of, decomposing the product of relatively prime numbers. So, for example, say we take U of 385. What is that isomorphic to? Can we figure it out without making the Cayley table? I hope we don't have to figure out the Cayley table. First, come up with a prime factorization of 385. It's 5 times 7 times 11. Double check that. Yeah, that's right. 5, 7, and 11 are all relatively prime. This is going to be isomorphic by this fact here, extended to 3, the product of 3 things, to the external direct product of U5 with U7 with U11. But what are those isomorphic to? These are all prime numbers, 5, 7, and 11. Certainly this thing has 4 elements. It might be isomorphic to Z4, though it could be isomorphic before the fact to Z2, external direct product with Z2. This has got 6 elements, this has got 10. Altogether we are going to have 4 times 6 times 10, 240 elements. But what is it isomorphic to? There's another fact here on the next slide. You can use this thing. In all these cases, n is 1. So these are cyclic of the appropriate order by that last fact right down there. This is isomorphic to Z4, external direct product with Z6, external direct product with Z10. 4, 6, and 10 are not relatively prime, so this is not cyclic. Could I write it any other way? Yes, I could. I could also write this as this. I did mention the other day that with external direct products, you can switch around the orders of the factors and you still get the same isomorphism class. So I could also say this is isomorphic to, for example, this. You can do that switching around of the factors in the external direct product, even if the individual groups are not abelian. No matter what G and H are, the external direct product of G and H is going to be isomorphic to the external direct product of H and G. Again, the isomorphism just switches around the components. And you should be able to prove that's an isomorphism. It's not too hard. And that can be extended to a finite number of factors. Not cyclic. It's isomorphic to any of these. This is probably the simplest form. And using this, you could figure out the number of elements of various orders. That would be the most useful representation to have to figure out the number of elements of various orders. It would be kind of a pain because you got 3 factors here. But it's doable. How about this one? If you compute the prime factorization of 225, it's 3 squared times 5 squared. 9 and 45 are 25 there. By the fact in the previous slide, this is isomorphic to this. And now by the fact that you see right here, once again, each individual factor here is cyclic. Now n is 2 instead of 1. So in the case where p is 3, you're going to get 3 squared minus 3 to the first. 9 minus 3 is 6. This first thing is isomorphic to Z6. And in the case where p is 5 squared, you're going to get 5 squared minus 5 to the first. 25 minus 5, 20. This is going to be Z20 here. That tells you right away this has 120 elements, 6 times 20. And once again, if you made a table and thought about least common multiples, you could figure out the number of elements of each order. Not quite as much of a pain with this one as the preceding one, because you only have 2 factors here instead of 3. And once again, for emphasis, I can switch these around. I can also break up the 6 and the 20 into prime factorizations. The 6 I could think of as 2 times 3, and I could write this. The 20 I could think of as 4 times 5, and write this. These are all relatively prime, so this is all okay to do. I can't break that up into Z2 external direct product with Z2. Because the Z2 external direct product with Z2 is not cyclic, because 2 and 2 are not relatively prime. This is not isomorphic to Z4. So I can't break that up. It's a little tricky, but if you practice it enough, you'll get it. Okay? Just make sure you do some practice. Probably on a quiz, maybe today, maybe next time, you'll have to think about this kind of thing. I think on the exam, second exam, it's definitely going to come up where you'll have to have enough practice that you feel comfortable doing this kind of thing. There are also facts about these things that come up. I don't want to spend time with it today, because I want to get on to other content. Maybe we'll come back to this on Wednesday. When K is a divisor of n, you can define this thing, which is, remember, a subgroup of un. This is best thought of with examples. So So look at the book's examples, make up your own examples. Think about this. You can also say these isomorphism facts. All right. For the rest of the time before the quiz, we're going to go on back to normal subgroups. And then after the quiz, we'll talk about these factor group things. So once again, what is a normal subgroup? A subgroup H of a group G is called normal. A normal subgroup of G, or is said to be normal in G, if every left coset is also a right coset. The left coset containing A and the right coset containing A are actually equal. They always both contain A, for any A, but they're not always equal. When they are equal, then we say it's called a normal subgroup. Again, you should be able to say this in words. For every A and G, the left coset of H and G containing A equals the right coset of H and G containing A. We got the special notation. Put this extra line on the subgroup symbol. That is a very commonly used notation. Okay. I mentioned some examples last time. I'll mention them again. The most fundamental examples right off the bat. If G is abelian and H is a subgroup of G, then in fact H is a normal subgroup of G. That should make sense. It's abelian. For any element in this left coset of the form little a times little h, you can switch them around. That's the same as h times a. And therefore will also be in the corresponding rights coset. And that's true for any arbitrary element in here. These will be equal, therefore. So with abelian groups, any subgroup is normal. In general, if G is a group, abelian or not, then the center of the group is always a normal subgroup of G. Though the center could be trivial, right? It could be just the identity. The center of everything in G that commutes with everything else in G. It might just be the identity that commutes with everything else. That is true, for example, with D3, for example. It's just the identity. D4 has more than just the identity in the center. It's got the identity and also R180. This is a normal subgroup of D3. This is a normal subgroup of D4. Whether G is abelian or not, the center is going to be normal. Because this kind of equation is going to be normal for all H in the center. H being in the center means it's going to commute with everything. And trivially, no matter what your group is, the trivial subgroup is normal and the whole subgroup is normal. Here's another fact that I think is worth knowing. It comes up, I think I assign it as a completion problem. Okay, this is definitely worth remembering. If G is a group and H is a subgroup of G with the index of H and G being 2, meaning what? What does that mean? What does it mean for the index of G and of H and G to be 2? if there are two what? Don't remember? Nobody? The index was defined to be the number of left cosets of H and G. If there's only two distinct ones, visualize it like that, say. If there's only two distinct left cosets, also two distinct right cosets, then H is going to be normal in G. That's worth knowing. And you may, after this chapter, you may use it whenever you might need it. If G happens to be finite, if G is finite, this equals the order of G divided by the order of H. Right? That's Lagrange's theorem. Or more specifically, actually, the proof of Lagrange's theorem. Again, I point out this note. We'll come back to this maybe next time. Evidently, this definition holds out the possibility that being normal in is not transitive. Just because H is normal in K and K is normal in G may or may not, I'll put a question mark here, may or may not imply that H is normal in G. This definition holds out that possibility because this is supposed to be true for all A and G. So if this is true for all A and K, meaning this is true is what I mean, for all A and K, and something similar is true, AK equals KA for all A and G, it's not necessarily true, seemingly, that this would be true for all A and G, that H would necessarily be normal in G. You might hope this would be true, but maybe it's not. It's certainly true if I just replace normality by being a subgroup. Being a subgroup is transitive. Just like there were subgroup tests, there's also something called the normal subgroup test. A subgroup H and G of G is normal in G if and only if XH X inverse is a subset of H for all X in G. We've seen this before. XH X inverse, we wrote that before except with an A. This would represent all products of this form as little h ranges over capital H. If that's a subset of H for all X and G, then H is going to be normal in G. It's an infinitely. So if this is a subset of that, then H will be normal in G, and conversely, if H is normal in G, then this will be a subset of that. And that also means if XH X inverse is not a subset of H, then H will not be normal in G as well. Here's a way you can write it in symbols. Being normal is special. We're going to see it's extra special in lecture 2. It's the main reason why it's special, I should say. Actually, this is worth knowing as well. For any subgroup H of G, normal or not, this set XH X inverse is another subgroup of G. Or it could be the same subgroup of G. So when H is normal in G, this is actually going to be a subgroup of H. In fact, it's actually going to equal H, which we actually already knew. Property of cosets. One of the properties of cosets that was listed in that lemma with all the properties listed was that if, or AH equals HA if and only if AHA inverse equals H. That was a property of cosets. That's for an arbitrary element A in G. If this is always true, if it always equals H, no matter what A is, then H is going to be normal in G. Before the quiz, I think it's worth verifying this last statement that I made. If H is a subgroup of G, I'm not talking normal subgroup now, just an ordinary arbitrary subgroup, then XH X inverse is also a subgroup of G for all X in G. Not necessarily equal to H, it would only equal H when H is normal in G. We can use the 1 or 2 step subgroup test. Let's use the 2-step subgroup test. The identity is in H, and therefore XE X inverse, which equals X X inverse, which equals E, is also in H. Well, and this is also in XH X inverse. That's all I really needed. So XH X inverse is non-empty. That's what I was just trying to say. And that's all I really needed to verify it's non-empty. You got 2 elements in this thing. Is there a product in the thing? Is it closed? What does it mean to be in there? It means there are elements H1 and H2 where A is XH1 X inverse and B is XH2 X inverse. And that will imply that A times B is XH1 X inverse, XH2 X inverse. These things cancel to give you the identity. This gives you XH1 H2 X inverse, and that is definitely in X capital H X inverse, since capital H is a subgroup of G. So this set is closed under multiplication. Is it closed under taking inverses? A is an X H X inverse. Is A inverse also in that set? Well, what do you think you need to use here to show that? Take a guess. What do you think you're going to need to use? Here's a little hint. Is that not enough of a hint? Or is my butt, I'm not looking like I'm actually trying to take off my shoes. Sock shoes. Or I guess in the case of 3 things, sock shoes galoshes. It's kind of sloppy today. We got some snow last night. And this is in X capital H X inverse. Again, since H is a subgroup, H inverse will be in H. So this statement here is true. This verifies the fact here. This is a fact worth knowing too. Okay, let's take the quiz.